as much as low as possible. Okay, now what happens here is, for example, you take the case of a nuclear power plant raft. When we are placing the concrete, the raft could be around, say, 1,000 cubic meter total volume. It cannot be done within a day. It goes for maybe 2-3 days, let us say. In that case, certainly you will be experiencing variation of temperature of maybe 5 to 40 degrees centigrade. So in that case, what we do, we replace water with ice or ice flakes. By replacing water with ice flakes, we are reducing temperature of concrete from its normal temperature of 34 degrees to as low as even 12 to 15 degrees at the mixing, that is at the batching plant. And to achieve this particular temperature is not only the a replacement of water with ice, we even cool the aggregate in the bin of that batching plant. And sometimes it may so happen when the temperature of ambient temperature is quite high, we may have to replace 100% of water with ice, 100%. Here, one point I'd like to mention about replacing water with ice. Ice means we cannot add ice cube in concrete. Simple reason, because when you add, let us say, ice cube in concrete, temperature certainly would come down. But when you place a concrete in the form, the cube would not have melted yet. And by the time it melts, you might already place a concrete, and once it melts, it forms a void in concrete. So that's the reason why we go for ice flakes, thin flakes. So by the time the concrete is taken to the site and it's pumped, by the time the ice would have already melted and it will become water. Okay? And then pore height. Now, as per IS code, the pore height, or you can say the free fall of concrete, should not be more than 1.5 meters. The reason is when the concrete falls more than 1.5 meters free fall, there are chances of segregation. So to avoid this free fall to be more than 1.5, when the height of the pore, nowadays when nobody uses a formwork of 1.5, 1.6 meters, always 3 meters, 4 meters, sometimes even tall structures we pour in single pore. In such case, what we need to do is we have to put a trimmy pipe right up to the bottom, pour concrete and go on lifting it like we do in a pile foundation. So the free fall is reduced. This would happen if the reinforcement allows you to put the trimming. So all the more important, the designers, when they're designing a structure, to keep in mind that the reinforcement, let us say if you take a column, the rings are kept in such a way that there is a place for inserting the trimmy pipe. The diameter of pipe will be as big as even 5 inches to 6 inches. So we need to have a gap of that much gap for pipe to be placed inside and then for pouring concrete. So the reinforcement detailing should take care of this. The last is durability. Of course, it's very well defined in IS code. The durability depends on the exposure criteria, right, from mild to severe and extreme severe conditions. So based on that durability criteria, cement content is mentioned, minimum cement content is mentioned, water cement ratio is mentioned in the IS code. Follow it, it works. Now, we talked about general properties of concrete, which is applicable to any general structure. But let us say, what happens in a nuclear power plant? In addition to what was shown in the previous slide, these properties are at most importance for nuclear power plant. The first is split tensile strength. Now, split tensile strength comes into picture where the concrete undergoes tension. And normally we neglect tension, okay? But there are some structures, I'll explain in a later part of the slide, that there are some structures where tension will come in picture in concrete, okay? So that's where we need to understand split tension, particularly the curved structures, like our containment wall, curved wall, or our dome. It needs split tensile strength, and we need to test it and maintain that the requirement. Flexural strength, of course, yes, is required, because again, flexural strength again comes down to the tension in concrete. Consistency. This is a very important aspect in a nuclear power plant. We have to have consistent concrete. Concrete should be consistent, and throughout the building, throughout the particular structure, the concrete should be of consistent quality. To achieve the consistency in concrete, we follow a special code known as RCC-G. I'll explain about RCC-G later. Creep and Young's modulus. These are required in, let's say, nuclear power plant. The reason is that now we are using a pre-stressed concrete, we are using pre-stressing cables in the inner containment wall. Creep of concrete plays a major role when it comes to pre-stressed concrete. Young's modulus comes as a major role also. So we test both of these, we record them and ensure that the creep and Young's modulus of concrete are well within what the code allows us. Now let us talk about RCC-G. Now, what is this RCC-G? Well, actually, what I'd like to give some background about this. When you talk about concrete, we have our own Indian standard codes, IS codes are there, where we have a code for mixed design also. We do a mixed design, we produce concrete, we use it. This is as far as normal structures are concerned. When it comes to nuclear power plant, NPPs, the requirement of the qualification concrete is not as simple as what the IS code says. So there's a special code. This code has been formed by the nations, the nuclear nations we call them as, all those nations who have got nuclear power plant, they are all members of this particular committee. And this committee has formed codes for all aspects of nuclear power plant, not only civil, could be electrical, mechanical, piping, could be anything. So RCC-G is design and construction rules of civil works of a PWR nuclear island. It is basically, RCC-G is basically for civil works. And there are, like this, there are a number of other codes for other works also. Now there's something, but one word I used here, PWR nuclear island. PWR means pressurized water reactor. Before I go down to further slide, just want to give you a brief about the types of reactors, though it not be so relevant to this particular topic today, but just as a background. There are different types of reactors worldwide. In India, the first reactor that was installed was Ramco in Maharashtra, Unit 1 and 2, which was a boiling water reactor. Right? These days, boiling water reactors obsolete, they're not being used. In a boiling water reactor, the reactor coolant boils within the reactor, steam is produced, the steam goes to the turbine. There was a lot of problems in a boiling water reactor. Pressurized water reactors. Now, in pressurized water reactor, there are again two types. We have pressurized heavy water reactor and pressurized water reactor or normal water. India, we using only pressurized heavy water reactors. We're not using PWR. PWRs, Indian technology, we don't have PWR, but we have imported PWR for Kodankulam from Russia. So today we have PWR also, and there are some more plants coming up in PWR in the future. Coming back to PHWR, which is Indian technology, which we have completely mastered, we are using heavy water. There's a slight difference between PWR and PHWR. When you're using a PWR, pressurized water reactor, where it is normal water, H2O, you need enriched uranium. Uranium, what is available in the ore form, natural form, is in that the fissile material is hardly 0.7%. Only 0.7% of the uranium what you get in nature is fissile. Whereas if I use that kind of uranium in a pressurized water reactor where normal water is a coolant or normal water is a moderator, there this kind of uranium cannot work. So we need enriched uranium. So what we need to do is we have to have enrichment. In India, we have not yet developed that technology, though it is in process, and we are almost reached a stage where we say that a stage of enrichment. Whereas when you use a PHWR, heavy water reactor, we don't need enriched uranium, we can use natural uranium. So all our Indian nuclear reactors are all PHWR, heavy water reactors, we are using natural uranium. The next generation of reactor is called a FBR or fast breeder reactor. We already got a fast breeder reactor in Kalpakam of 500 megawatt. Earlier, we had a fast breeder test reactor wherein we did a lot of testing on the reactor, understood its performance, and then now we started working on a main reactor of fast breeder reactor. The difference between a PWR and a fast breeder is that in a fast breeder, the uranium, the fuel breeds, the reactor breeds the fuel, so we get a breeding of uranium of fuel, due to which we are going to get better power. Okay, so let us not go further down into it. So this particular code RCC-G is a design and construction rules for civil works of PWR nuclear island. So it says PWR, the rules given in this book is applicable to any nuclear reactor because it doesn't differentiate between PWR or PSWR. The way we use the concrete, the way we use all the civil, the code in civil works is applicable to all reactors. Now, what this code tells is talks about only qualification. So that means you should have already established a mix as per your country code. In India, we have our own IS code which talks about the mix design. We have to establish the mix as per our Indian code. Simple. The first step that we completed, let us say. So what it says is to ensure that properties of mix remain same with the variation of manufacturing process. This is a basic of RCC-G qualification. You have designed the mix. You establish the mix design. Now this mix design should remain the same with variation. Now the variation comes due to tolerances. Say you go to batching plant. Batching plant has got a tolerance of around 1 to 2%. So due to the variation, the consistency of the concrete should remain constant. For that reason, various test requirements are provided in RCC qualification. These test requirements actually account for lab conditions, manufacturing process, environmental conditions, and actual material being used at site. Okay, there are 3 tests that we need to do as per RCC-G: qualification test, acceptance test, and information test. Let us see each of them what they are. Qualification test. The purpose is to check that designed concrete mix. Design means, again I'm telling that as per IS code you have done the design already. Design concrete mix meets the specified requirement. Yes, this is simple which is known to all of us. But in addition, to ensure that these requirements are met, even when the ingredient proportion correspond to the tolerance limit. So even with the tolerances also we are supposed to get the consistency. Now this particular qualification test is done in lab condition. So this is the first stage. So we do in lab condition. What we do, we take 3 mixes using exact mix proportion as per IS standard, as per IS mix design. Then one mix each of plus 10% and minus 10% variation in stand. 2 mixes each of plus 25 kg, minus 25 kg variation in cement content. So we got this many mixes, that is 3 plus 2, 5, 5 plus 4, 9 mixes we are done for qualification test. These mixes, what do we do now? This is the acceptance criteria of qualification test. Shall meet density and slump criteria. Coming to the FCK, average 28-day compressive strength for the design mix shall satisfy the following 3 conditions. Now the conditions are given here. Let us go down to what it says. FCE is an average 28-day compressive strength of 3 mixes using design proportion. As per IS, you have done the mix design. You conduct test on that your exact proportions and for 3 mixes and find out the average compressive strength. That should be equation number 1 greater than FC28, means use FCK. In RCC called as FC28. Indian codes it says FCK. So it's FCK plus CE. What is CE? 28-day compressive strength of cement used in MPA. So we are bringing in cement into it. If you refer to IS 456 acceptance criteria, cement strength is not at all a criteria. It's only standard deviation. FCK and standard deviation and 2 things are available. Here we brought in cement into it. If CE is 28-day compressive strength of cement used in MPA, and C mean is past 6-month average compressive strength of cement. Now, this is another critical thing that why we brought this. RCC is talking about this is you will be having a go down. You'll be storing cement with you. You're going to consume cement from there, and you're going to get cement maybe from number of manufacturers. Who knows? There is a possibility today from ACC, tomorrow from Ramco, or third from Ultratech. It may happen. So you need to keep record of the strength of cement in the past 6 months. That gives the consistency of cement. That is factored into the formula. Minus 3, yes, is a standard deviation, plus 3. This is the first equation. Second is FCE should be greater than 1.2 times FCK. Third, 28-day compressive strength of modified mixes. Now, FCE was on the exact mixed proportion. Now, let us come to the modified mix. This we talked about the variation of sand and cement. So these modified mixes shall be within plus or minus 15% of FCE. So these are the 3 criteria that we need to meet of the mix design which we have already devised as per IS code. And all this is on laboratory condition, laboratory test, laboratory mixing machines, and done in laboratory. Now let us see the next test. It is acceptance test. Acceptance test, actually now we move from lab to site. What we do here is we go to field conditions. We take the mix design from the lab, go to the field condition. Whatever machine you're using at site, could be batching plant, could be a mixer machine, could be anything, whatever you're using at site. Use that machine as it is, and all the material that are going to, actual material they're going to use in the site. Because in the lab, you might have taken a few bags and brought it there to laboratory and done the testing. In the site, the batching plant will begin truckloads of material. So use the material as it is coming into the batching plant. using these two due to concrete mix design, mix testing. What we do is 3 concrete mixes using designed proportion. Design means again IS standard, are produced at batching plant using the same ingredients which are proposed to be used in actual construction. So that means you're trying to qualify the batching plant. It's a field condition. What we do, these 3 mixes, we determine slump, unit weight, and air content on the green concrete. On hardened concrete, determine compressive strength of 7-day and 28-day along with split tensile strength. All the 3 we do, we test it. Now let us see what is the acceptance criteria. Requirement of 80. 80 means acceptance test. Average 28-day compressive strength shall satisfy the following 2 equations. These equations are similar to the earlier 2. Let me go back to the earlier slide. The first equation was having +3 and the second equation is same. So here when you come back to this slide, the +3 is removed. That means they are given a margin. In laboratory, it was all very highly controlled conditions, so that +3 was there. FC should have been more than so and so +3. So if in site condition, in batchment condition, that 3 has been removed, there is some margin given to you so that you can qualify the mix even in batchment condition, because in batching plant there could be variations. To take care of the variation, this formula has been slightly tweaked. Second equation is same 1.2 times FCP. Then check the yield of concrete, which is a normal process that any batching plant, anybody does check the yield of concrete. The third is quite important. Conduct field trial to simulate the site condition of concreting such as pipeline, configuration, etc. and carry out wet sieve analysis. What we do here is, now let us say I have to do the concreting of dome which is 50 meter high above the ground. Now I have to transport concrete from the batching plant which could be a kilometer away. So I bring concrete from the batching plant in transit mixers, pour it into the pump. Pipeline is laid for maybe around 10-15 meters horizontally, 50 meters vertically, and maybe another 10-15 meters horizontally till it reaches the pouring point. We simulate the same condition. We lay the pipeline the same condition. We use the same pump what we are going to use it during concreting. Bring the same concrete from the batching plant, pour it into the pump it up. Before we pump it, collect the sample from the transit mixer, conduct wet sieve analysis before pumping. After pumping, go on top where the concrete is coming out from the pipeline, collect concrete there also and conduct wet sieve analysis. This actually is trying, what we are doing is we are trying to establish consistency in the field condition itself. From the time we pump it to the top where it reaches the top, between that there should not be any change in the consistency of concrete. The next slide shows you a test done in one of the nuclear power plant. It was done for M4520. Normally in nuclear industry, we name the concrete like this only. M45 means 45 grade, 20 means size of aggregate. So it's M45 grade concrete, 20 means size aggregate. This has been done for wet sieve analysis. The blue line says before pumping, red line says after pumping. But you see the blue and red almost as merged with each other. That means concrete before pumping and after pumping is consistent. This graph actually is nothing but the sieve analysis graph. It's giving the percentage passing of the material. But why we are doing wet sieve is because we wash the concrete. We take that concrete and wash it, remove all the cement and all the fine particles from there, and then do the sieve analysis so that we find out the aggregate percentage passing at pumping versus after pumping. Okay? So this is acceptance test. With this, what happens is we have qualified the concrete. Now we have done the qualification test, we have done the acceptance test. So the mix design which was done as per IS standards has been qualified. Once this is qualified, now we'll move to something called information test. Information test actually is to identify if there's any problem in concrete during the process of construction, identify the problem as early as possible so that we can rectify the concrete. Maybe it could be in the mix or could be in the batching plant or whatever it could be. For that, what we do, we collect some data of the concrete. So before we start our work at site, what we do is we carry out mixes of 3 mixes using exact mix proportion as per our mix design. 2 mix each with -25 and -50 kg variation. So the variation is quite high. 25 and 50 is certainly nobody will expect such a high variation anywhere. But still, we try to go to the extremes of -25 kg and -50 kg. 2 mix each with +10% and plus 20% variation in water. Again, that's also quite high. 2 mix each is minus 25 kg and plus 10% water. Again, mixture. And minus 50 kg and plus 20% water. These many mixes we do. 3 plus 3, 3 plus 6, 9 mixes we are done. Now we find out what is the compressor strength of 3-day compressor strength of this particular, each of this mix. It could be either 3-day or by using accelerated curing method, we go for 24 hours also. Okay, so we have established the 3-day compressor strength. This data is kept as a ready reference record for us. Okay, now what we do when we are doing the concreting actual work, there will be always a sampling criteria decided between the contractor and the client. Based on sampling criteria, maybe let us say every 50 meter cube, you are supposed to take one sample for 28 days time. You will be taking a sample for 28 days time. During that time, take 3 samples for this IT also. These 3 samples, what we do, we test it for 3 days time. These 3 samples we take and test it for 3 days time. Either we wait for 3 days or by using heated curing concrete, by that method, you can do 24 hours also. So we establish the 3 days strength of concrete. If that particular strength does not meet the criteria, what is the criteria? Average of all whatever we have done in the previous, all these variations, all these mixes, average of all that, we take the average. This particular 3 days should be more than the average. If it does not meet the criteria, then the contractor will be asked to check all the parts of the batching plant, the concrete production equipment, then even the transportation, the material, everything he checks, and he does some tweaking to ensure that we again come back online. But if this repeats once again, then stop the concreting, stop all activities, and investigations done. What we do here is we are trying to identify the concrete strength as early as possible. So what happens is, if let us say I wait up to 28 days time, till 28 days, this batching plant would have produced a number of concrete, maybe thousands of cubic meter of concrete would have produced, and all would have been used in number of places. If identify after 28 days, you would have lost a lot of time, and all that structures which have been poured, maybe we have to dismantle once again. So to avoid that, we try to identify this problem as early as possible. So we stop the concrete, do investigation, and then we proceed further. So this was the basic requirement of RCC-G code. It talks about various tests on concrete. This actually brings into picture of the consistency of concrete, how to maintain concrete consistent enough for a nuclear power plant. Now, why I'm talking about consistency, a nuclear power plant actually always has got redundancy. In everything, there's redundancy in nuclear power plant. And the safety is utmost important in nuclear power plant. First comes safety, next comes money. So we always try to put safety in front of us. So keeping that in mind, we always ensure that whatever we do in a nuclear power plant is safe. We have to ensure that there should not be any release of activity from the reactor building to the people outside. That's a foremost important thing that should keep in mind in a nuclear power plant. So concreting, whatever we do as per RCC-G code, the quality control measures, quality assurance measures are always in place. And even while placement, we take care that the concrete is compacted perfectly, properly. If there's any problem, we find after deshattering, we simply dismantle that structure and redo it as simple as. Okay, there are nothing called repairs. Minor repairs we can do, but if there's a major thing, just dismantle, redo it. Okay, so we talked about the requirement of RCC-G code on concrete. Now let us talk about different types of concrete that are used in a nuclear power plant. Of course, normal concrete is already there, so I don't want to talk about normal concrete. Skipping normal concrete, I'll go to other concretes. We have something called high density concrete. High density concrete is actually density which is more than 3,200 kg per cubic meter. A normal concrete density is 2,400 kg per cubic meter. It is known well in us. So anything more than 3,200 is called as high density concrete. Why high density concrete? I'll explain later in further slides. But how do you achieve this kind of high density? In a normal concrete, we use normal aggregates. In Karnataka, we will be using granite as a good source of aggregate, and even the crushed granite also could be used as a fine aggregate. So granite stone, if we use as aggregate, we can achieve up to 2,400 kg per cubic meter. But when I have to increase the density, I have to increase the density of the ingredients in concrete. One method could be use lead shots. or use steel shavings in concrete. But by using these kind of very high density material, there's a possibility of segregation. Let us say I use lead shards in concrete. The lead shard may settle down and may not be in a state of suspension in concrete. So I may lose the requirement of density of concrete when I use lead shards in concrete. So what we go for is we go for high density aggregate. One of the best high density aggregate could be iron ore. The cheapest, I would say. Simply go to iron ore mining and get iron ore from them. Bring it to your crushing plant, crush the iron ore to the size of whatever size you want. 21 aggregates, you crush it. You can further crush it and make it sand also. So iron ore as a coarse aggregate, iron ore as a fine aggregate is used. We don't use anything other than this. No granite and nothing is used here. So use iron ore as aggregate and mix it in concrete. You're going to get a density of easily 3,400 kg per cubic meter. Even in some places, we get even 3,600 kg per cubic meter density requirement is also there. This is called as ultra high density concrete. So higher the density of concrete, we go for higher dense material used in the concrete. Okay, and as I said, density is 1.5 times the density of conventional concrete. So excellent shielding material can attenuate neutron and gamma rays. This particular aspect I'll explain in the next slide. Aggregates, as I told, can be made out of barite, magnetite, limonite, hematite, etc. In Kaiga, we use hematite aggregate. It is available from Bellary. We used to bring hematite from there, crush it at site and use it. Steel shards and punching is also used, but in a very small way. As I told you, it may lead to segregation. Now, since heavy density concrete are using concrete, it may aggregates using concrete, it may exhibit tendency to segregation. Because naturally, if steel shards can segregate and settle down, even hematite also can happen. Okay, so we have to ensure that concrete is in suspended stage, that it doesn't get segregated. For that, we have to conduct a lot of trial studies on the mixed proportion to get a concrete which keeps the aggregate in suspension and it is pumpable also. It should be pumpable. There's always a problem in pumping high density concrete that the pipeline may get worn out. Yes, it may happen. That's one part of it. But otherwise, make it pumpable, because we have to place concrete in such remote areas where you can't carry concrete, either with manual or by crane. Okay. So now let us talk something about the physics of a nuclear reactor. This is connected to my earlier slide of attenuation. What exactly happens in a nuclear reactor? There are two types of reactions that may happen, either fission or fusion. Both reactions are related to nuclear. Okay. Fission reaction is what happens in a nuclear reactor. Fusion is what is happening, I'm telling you, in sun. Where two atoms combine together and they become one atom. That's a fusion reaction. In a fission reaction, what you see in the slide, uranium atom is splitting into two. Okay. Now, fusion reactors are also being thought of, and the technology of fusion reactor is getting developed. India is one of the country, a member country, who is developing a fusion reactor. Maybe in the next decade or so, we may come across a fusion reactor. Fusion reactor is like, handling sun in your hand, and then you're going to have abundant energy. Whereas, let us talk about fission reaction today, what we have with us. Fission reaction is something very simple. Uranium ore, let us talk about. Uranium ore consists of various forms of uranium. Okay. It could be uranium-235, it could be uranium-238, and it could be uranium-239. Now, out of these three, uranium-235 is fissile material. And this I told is hardly 0.7% is available in any ore of uranium. Uranium-235, when it is hit with a neutron, now that number 1N0 is a neutron. Similarly, when you look at uranium-235, 235U92. 235 and 92 are representing the atomic number and atomic mass. So when a neutron hits a uranium atom, that uranium absorbs the neutron from 235 becomes 236, and it becomes unstable. Now, unstable means every element. If you go to Mendeleev's table, in Mendeleev's table, he has given the list of all the elements. All those elements are stable elements. When a neutron hits or enters into a nucleus, then becomes unstable. Anything which is unstable raises its energy level, and then it cannot stand in that condition. It has to come down to stability level. So something to become stable once again, it has to split into two or undergo some other mutation. So in fission reaction, it splits into two, and as krypton and barium. In the process of the splitting, it gives us energy in the form of heat. That's what I talked in the first slide, that heat is produced in the nuclear reactor and taken by the coolant. This energy, heat energy, is taken from there. But in addition, it is giving something else also. It is giving gamma rays and giving another 3 numbers of neutrons. Gamma rays and neutrons are actually radioactive material which can cause harm to a human being. So this particular fission reaction is now leading to something which is harmful to human being. So what do we do now? Types of radiation. There are actually different types of radiation, which is alpha, beta, gamma rays, and neutrons. If you take, let us say, uranium ore, from the earth you take uranium ore, it will be, certainly uranium ore also is actually radioactive. It will be giving out alpha and beta radiation. Uranium ore, if you are holding in a hand, you're not going to damage your hand, you're not going to die. Okay. But when the same uranium is used in a nuclear reactor, fission reaction happens, then gamma rays and neutrons are coming out of it. That is going to be damaging the human body. Now, like if you go back to Madame Curie, what the experiment she did, she used radium and she was doing a lot of experiments. At that time, she was not aware of all this radiation, and then during the process of experiment, she found out about the radiation, but by the time she got exposed to radiation, and finally she died of cancer. Okay, so radiation causes cancer. So how do we stop this from affecting the human? Now, each radiation I put in front of that, what all material can stop the radiation? Alpha radiation can be stopped by paper or doesn't even pass through your skin. Beta radiation, thin aluminum foil is enough to stop it. Gamma rays will require high density material such as lead, steel, etc. Any high density material, gamma rays can be stopped. Neutron is reverse. It requires low density material like hydrogen, boron, etc. Now, this particular mixture of high density and low density is possible only in concrete. Concrete is the only item which can give you both. How? I am adding aggregate in concrete, maybe hematite aggregate, high density, and I'm stopping gamma rays. I'm adding water in concrete, which consists of H2O, hydrogen H2H is available in water that can stop neutrons. So concrete is one item, one material which can stop both, and we call concrete as biological shielding. That's the name used for concrete. It's just whatever explained in the previous slide in a more pictorial way. You can see that all the 4 radiations can be stopped in this. The last is concrete. If you don't put lead, gamma ray can come up to concrete. I have to make concrete as heavy density, then I don't put lead. This is one way of stopping the radiation. We don't call radiation can be stopped. It cannot be stopped, first of all. Radiation is energy. It can be only attenuated. Attenuation means reducing the power of radiation, bring it to the level which can be handled even if it enters human body, should not harm the human body. So we should attenuate and bring it to such a low energy. There are 3 principles of radiation protection. This is important for we civil engineers to understand. Time, distance, shielding. What time means? Less time spent near the radiation source is better. That's why the person is running away. Don't spend too much time. I told you that the maintenance people go inside the reactor building for maintenance of the plant. Everything is controlled by control room. They don't go in horde of people of 100 people. No, never. There will be hardly 3 or 4 people going inside. When they go inside, they will be spending as less time as possible inside the building. So what is normally done is that the people are sent in batches. We send the initial one batch of 3-4 people inside. They do some maintenance for 1 hour or half an hour. They come out. Then next batch goes inside, does the maintenance, they come out. So this is how we control the time. The less the time is spent inside, the better. It doesn't mean, I don't say that the person who is entering inside the reactor building is going to get exposed to radiation. Not at all. But there could be chances of exposure. To avoid that chance, even to that extent, we don't allow people to go inside just for any reason. Distance. Farther from the radiation, better for you. So let us say if you take, say, X-ray. X-ray technician, he puts you in front of the X-ray machine and he goes and stands behind the X-ray machine or far away in one corner. Then he presses the button. So he is keeping himself far because he has to take X-ray every day. 10-20 X-rays he has to take. For you, just one X-ray. So he has to stand away. So distance, further the distance, better for you. Third is shielding. We talked about biological shielding. So this biological shielding is one aspect where shielding is required. It can be biological shielding, it can be any other method, but shielding is required when you have to work for a longer period in front of a source. Okay, so that's the reason why there are some areas in reactor building which is having not accessible and accessible areas. Non-accessible areas, I got a wall all round, a shielding wall all round, thickness of wall, normal concrete wall, forget about heavy density concrete wall. Thickness of wall in reactor building is as high as 1.3 meters. The reactor wall, the core wall, is 2.5 meters. That's the thickness of wall. We used to walk inside the wall. 2-3 people will walk in the wall between the reinforcement for checking. So that's the kind of thickness of wall we're talking about. So more thick wall, better, because thickness gives you, one is shielding and it gives you a better density and radiation doesn't come inside. So these are the three principles of protection. This one slide which talks about attenuation of radiation in a nuclear power plant. When you are putting a shielding wall, a concrete shield wall you put in between. Let us say this particular line is the line of the core of the reactor. Very high radiation is there. Within that core of the reactor, water comes out, slight attenuation has happened. But you can see a sharp reduction in the power of the radiation in the concrete shield wall. If the concrete shield wall is more thicker, then this could go maybe even to zero also, very close to zero. So thickness goes on increasing, the attenuation power goes on increasing. Density goes on increasing, this will be sharper and sharper. Now from here onwards, this is the air outside the concrete shielding wall. This is not the air which is outside the reactor building. This is the place where the accessible area, what are called, is this accessible area? This is a non-accessible area. In between, there is a concrete wall. Beyond this is our containment wall, and that completely cuts out this air, and no radiation comes out of the building, public or safe. Now, the stipulations of ARB is very simple. Allowable dose rate for occupational worker is 20 millisievert per year. Occupational worker is all those maintenance people who had to go inside the reactor building for maintenance. Whereas for general public outside the reactor building, it is 1 millisievert per year. It's 1/20th of what operational worker could experience. So that is the requirement. To attain this kind of requirement, we have to have enough proper containment so that the air from inside the building does not go out. I'll explain about what all we do to contain the air inside. Okay. Now, next step of concrete, we talked about heavy density concrete. Next is high performance concrete. Now, high performance concrete is something we can define high performance concrete as simple as this. As per ACI, it says concrete meeting special combination of performance and uniformity requirement that cannot always be achieved routinely using conventional constituents and normal mixing, tracing, and curing practices. What it means is, if you take a normal mixed concrete, we will not be able to achieve the high performance concrete by using these normal mixes. Navili has given a slightly better, I can say, explanation. He says, high performance concrete is concrete selected so as to fit for purpose for which it is required. There's no mystery about it, he says. No unusual ingredients are needed. And no special equipment is needed. All we use is an understanding of the behavior of concrete and will to produce concrete mix with closely controlled tolerances. So he explains so very clearly that we have to have the will to understand the behavior of concrete, then you can make an HPC. There's no special ingredients in HPC. So what is HPC? Relatively high strength as compared to conventional normal mixes. Yes, we know very well. For example, our IS code, now the grades of concrete of M45 and 50 are common nowadays. We don't call them as HPC. Earlier days, we used to call them as HPC. Now it's no longer HPC. We can produce it normal method itself. Once fresh concrete properties and durability aspects are met, next is the strength. So first you establish concrete with your durability aspects and your strength and your fresh concrete property requirement. Next, you concentrate on how to achieve the strength. So what we do? Say substantial reduction of quantity of water, mixing water is a fundamental step for making HPC. We have to reduce the water cement ratio. As the water cement ratio, the strength of concrete increases. And Neville says that you can bring it down to as low as 0.22 Of course, achieving 0.22 may be quite difficult, but it's always possible. So how do we do that one? By reducing water sedimentation, what do we do? We can add high range water reducer admixtures, and this becomes essential to have durability criteria because workability criteria. Because when they reduce the water content, it becomes unworkable. Add high range water reducer admixture to make it workable. Now, but when what happens is these admixtures are highly sensitive and very to bleeding. The high range water reducer admixtures, if you use it for reducing water to a certain extent of 0.22 or 0.25, then it may lead to bleeding. So, to avoid that, when the fine content in concrete is, that means it leads to bleeding when the fine content is less. So, what we do, we have to increase the fine content. This calls for additional fines as blendage to reduce the bleeding. But increase in cement is not advisable. Naturally, if you go for increase in cement, it increases the heat of hydration. So we have to add mineral admixtures such as silica fumes, fly ash. We need to add them as per your mixed design, mixed proportion, and add this mineral admixtures to increase the high performance concrete to get high strength concrete. Hence, when you think of HPC as high strength concrete, in addition to mandatory requirement of workability and durability, to consummate with the functional requirement, it is essential to introduce a pozzolanic material and high range water reducing agents like superplasticizers. So adding all these things, we can get HPC. There's nothing ingredient, any special ingredient is not required here. Add mineral admixtures like silica fume or fly ash, add superplasticizers, you won't get HPC. Now, the next type of concrete what we use in nuclear power plants is SCC, which is of course is very common. The days when we started using SCC, we were the pioneers in developing SCC. We developed SCC in our laboratory at Kaiga site and we used it. Then now it has become very common practice. People are using SCC world over everywhere. SCC can be defined as a concrete which flows as a whole mass without segregation. You can see the SCC, the concrete falling from the pipeline. A normal concrete, when it falls from the pipeline, it will be like a liquid kind of thing falling down. Here you can see aggregates also visible there, and it falls as a single mass. So this kind of concrete is SCC, that it should be falling down or it should fill the form as a single mass. Now we had conducted one test in Kaiga, wherein we had pumped this SCC from bottom of the column to raise it inside the column. It was a 3 meter height column. So from the bottom, the concrete raised up without pouring, without using any vibrator. We were able to fill the entire void, entire formwork up to the top without any segregation. We did a lot of tests and we found it was successful. Reduction in water binder ratio, limitation of coarse aggregate and its maximum size. These are all the requirements to produce SCC. Addition of mineral admixtures such as GGBS, fly ash, silica fumes. Use a superplasticizer. And addition of VMA. Earlier we were using VMA separately, but now admixtures are coming with VMA mixed in that. So we can directly use those admixtures. We don't have to add VMA separately. VMA actually is it makes a concrete to flow. Viscosity modifying agent. It makes concrete as a mass to flow in the form. Okay, so we talked about various concretes, different types of concrete that we use in a nuclear power plant. I'll take you through some of the facts and figures and some photographs. This actually is a table showing concrete used in a 700 megawatt reactor, RB's reactor building per unit. As I told you, always we go for pair of units. So per unit, what's the quantity and what's the grade? For the foundation, it's M45 grade, 42,000 cubic meters of concrete. It is not poured in single pour, mind you. It will be in multiple layers. Internal walls and slabs, M35, around 30,000 cubic meters. Look at the raft, 42,000, walls are hardly 13,000. Radiation shielding walls, M35, high density concrete, 6,000 cubic meters. Inner containment wall under dome is M45, 11,000 cubic meters. Outer containment wall under dome is M35, it's normal RCC, whereas your earlier one is PSC, precious concrete. So yeah, the outer containment is 99,000 cubic meters. All put together around 81,000 cubic meters of concrete per unit of reactor building is what we need. Let us go through some photographs. This is a 700 megawatt nuclear building raft concreting of M45 grade. I told you raft is poured in multiple layers. This is one of the layers the concrete is about to start or maybe just started. The reinforcement is tied. You can see 1, 2, 3 placer hoops and one crane here, one black color, it's used for crane bucket, and probably this tower crane is a standby. So this concreting is done from 4 locations, and we have poured concrete of the entire raft in one go, but one particular layer alone. And this photo is after that particular pour is completed, probably in the early morning hours. You can see now the pressure booms have got very close to each other. Maybe 2 booms are working there, and the crane is removed. This is high density concrete. You can see the concrete color is also red. Because we used emitted aggregate as aggregate, the color of concrete is red. This is part of the radiation wall or the reactor wall where concrete has been done. I can see the side vertical rods are still visible here. Here we can see the vertical rods of the wall. So one pour has been completed. These are the horizontal tie rods of the wall. This is a typical floor slab concreting being done in a reactor building. I'd like to explain about one particular aspect here. You can see some plates here. Here. Number of plates are there. These are basically the insert plates. Now, in any reactor building, a slab of, let us say, around 200 or 250 cubic meter concrete quantity of the slab, there could be at least 500 plates. That's the kind of insert plates that we install both to the soffit or slab on top of the slab. These insert plates are required for supporting all the systems. Could be piping, could be electrical cable trays, could be your fire water line, could be steam line, and even equipment also. In a reactor building, we try to avoid as much as possible drilling of anchor fasteners. People, if they're on this one, they may not like me, but yes, we try to avoid anchor fasteners, and we always say, like even Hilti guys also say same thing, that anchor fasteners are used for somebody does a mistake, then he needs anchor fastener. So in a reactor building, we try to avoid anchor fasteners and put insert plates as much as possible. We even have anchor bolts also installed in the slab. So by doing this, we are avoiding anchor fasteners. All the equipments and all the system lines are getting supported on insert plates. This is the same slab almost getting completed. What I want to explain here is, you can see that tarpaulin cover on top. It's not due to rain, but it's only to prevent sunshine, heat, the sun heat coming on the concrete, to prevent evaporation of water from the concrete. Second thing is, in the reactor building, all the slabs, they don't have any floor finish, they do not have any screed on top. The finish, what you do during concrete is final finish. There cannot be any further finish that can happen on the slab. On this finish, we directly go for epoxy painting. Now, in addition to finish, this particular slab will have slope. It won't be one level. There will be a number of drain pipes kept in the slab, and all the slopes are directed to those drain pipes. Why we need a slope in a slab here? Because, as I told, there will be a number of equipments, pipeline will be running all over. There could be leakage, or there will be some drops of water falling from some equipment or some pipeline. Any water that is coming in the reactor building within the containment could be, I'm telling, could be radioactive. So if it is radioactive, we cannot leave the water to get stagnated in one place, it starts emitting radiation. So we try to take the water into a drain pipe and take into a tank and store somewhere else. So these slabs will always have a slope and drain pipes, and the finish, the person who is doing the finishing here is doing the finishing and is rubbing it. So normally what we do after 5 hours of concreting, we'll put all the masons with patra, they go on rubbing till we get a smooth surface and till we get the slopes. This is one internal wall of a 220 megawatt wall reactor. Now, in a 220 megawatt reactor wall, here we can see the reinforcement. This particular wall is around 400 millimeter thickness. The reinforcement is 25 tall, both inner and outer face, and horizontal, vertical, all around 25 tall. That's the kind of condition of reinforcement we get in a wall. And the grade of concrete in this wall is M25. So these pours, normally we do it in 3 meter height, but recently we even started doing even 5 meters also, because we have developed SCC, we're able to manage it. So we're going for taller pours to have less number of construction joints. This is a base raft, reinforcement visible for base raft to 220 megawatt. The reinforcement in earlier days we're using 45 mm diameter rods, but now because of shortage of 45 and 45 is not normally being produced, we have changed out to 36. The spacing has been accordingly adjusted. Here the reinforcement is circumferential and radial, because this is a circular rack. And this depressed portion, what you see here, is the dressing gallery part, where we have the stressing gallery for stressing vertical cables. That gallery is going to come in this particular depressed portion of the raft. Okay. Now, in the nuclear power projects, we always do mock-up for each and everything. Whatever we do, first time if you are doing something, do a mock-up. By doing a mock-up, we are trying to understand that particular structure, understand its behavior, understand how to, let us say if we talk about civil engineering, understand how to pour concrete, how to tie the reinforcement, how to avoid congestion. Now, this particular mock-up we are done for IC dome, inner containment dome. Part of the dome has been created here in a full scale. Exactly the same thickness, exactly the same reinforcement, the same processing cables have been kept here. We can see the sheathing, they are all SDP sheathing. On the top where this person is sitting and tying some reinforcement, around him, this is the opening in the dome. I'll talk about this opening later. Our dome has got, in 220 megawatt, we had 4 openings. In 700, we have 2 openings. Opening in a dome means opening in a shell structure is always very critical. So I'll talk about it later, much later. So we picked an area of the dome around the opening, around 5 meter by 5 meter. We developed the shape using the formula. We developed the shape of the dome, socket shape. We have tied the bottom mat. The recessing cable, one direction has been already laid, second direction is in the process, and the top mat is supposed to come. After tying the top mat, we put the top formwork and then we pour concrete. After pouring concrete, remove the formwork, take 4 samples, test it, check it. We are confident, yes, it's okay. Then we proceed, else we repeat the mock. We did it. In one case in Kaiga, one of the mock-up we had to repeat because the method of putting the top formwork was we had a different method we tried and it didn't work out. So we dismantled that mock-up and read it once again with a different method and it worked. So mock-ups are done basically to understand how best we can pour concrete, how best we can tie reinforcement, what difficulty we are going to come across. In addition, when we do a mock-up, if we have a difficulty in executing the drawing, we go back to designer and say that this particular mock-up we have done like this, it didn't help us properly. Please change the reinforcement pattern or please change the processing cable pattern or whatever it is. So we give input to designers and designers will come back with a change in revision the drawing and it's executed. Okay, this actually is a photograph of reactor building in Kakrapara in Gujarat. You can see the reactor building here, circular building. This is the containment wall constructed up to the ring beam. We have a dome liner which is held with a crane. We are installing it on top of it. Now, this particular reactor building in Kakrapara has got a lining for even the containment wall also. The containment wall also is lined by steel liner. This dome liner is also steel plate. It is integral, it's part of the concrete. So this particular steel plate liner has got, you can see radial lines here. They are actually the beams stiffening the liner and making in the shape of the dome. It is brought and kept on top, welded at the ring beam level, and then reinforcement is tied. So this is installation of ISO dome liner. I think the weight of the liner was around 350 kgs. This particular dome liner, 350 tons, sorry. 350 tons of weight was lifted and kept. This is a photo of the IC dome during concreting. Liners installed, then we have tied the reinforcement, processing cables installed, everything completed, concrete is in process. If you look closely, you'll find that this particular red patch is an opening in the dome. This opening of the inner dome, if I just go to the previous slide, you can see same opening in the liner also. This is coming exactly and fitting on top of these 2 circles. Here, what you see is the boiler or the steam generator already installed. Now, if at all during operation we find we need to remove the steam generator for any maintenance, it is brought through this opening and taken out. So this opening cover will be removed. Say the same crane will be parked here. It lifts the boiler up and takes out. So openings are kept mainly to lower the boiler or lower the steam generator and take it out. So here we have the same opening here on the dome, one here and one in this side. So this opening has got a insert around the opening on which a dish end is going to be installed later. Now, what I want to explain in this particular concreting of the IC dome is this. The concreting has started somewhere here, and they are doing it on both the direction. There are multiple joints in the dome. One joint is somewhere here. You can see the joint in the dome here, construction joint. Second joint is going to come somewhere here. Then we have orthogonal joints on the dome. The dome is not cast in a single pour, it's done in multiple pours. The first pour from the ring beam to this first joint is being done. So we are doing concreting on both the sides using a placer boom here and a placer boom here. Now, this particular portion of the dome is very steep slope. The inclination is quite steep, it's more than 25 degrees. So when the inclination is so steep, we need to have top formwork. This top formwork is installed in position, concrete is poured. The installation of the formwork goes on progressively. You can see here the progressively they are putting the formwork and concrete is being poured, and the formwork is removed after 5 hours or 6 hours, and finishing is done. So here you can see finish completed, housing cloth laid on the concrete and moist curing is going on. Here in this portion, finishing is in progress. Here concreting is being placed. This is the second reactor building where ring beam level has been reached. De-sheeting is in progress. And for your curiosity, this is reactor building 3 and 4 of Kakrapara. This is 1 and 2 of Kakrapara. The very old reactor building, very old. You can see there's a large difference between this and this. Huge differences there. This is basically 220 megawatt. This is 700 megawatt. That itself is a major difference. Same dome, finishing in progress. I talked about top formwork. Up to this joint concrete has been done. While before concreting, we have installed these trusses. These are all steel trusses kept on the dome top, anchored to the soffit of the dome. And they are installed and aligned in such a way that the shape of the dome is attained. Between the truss to truss, we install these wooden planks. That's the top formwork plank. The plank would be 25 mm, 32 mm thick. The width of plank would be around maybe 250 to 300 millimeters. Distance between truss to truss would be around a meter. So we go on putting the plank, 3 plank at a time. Put 3 planks, pour concrete. Next, another 2 or 3 planks, pour concrete. Concrete is poured from the top into the plank and vibrated, and we proceed further. So from one end, if you go on pouring, the planks will be laid something like this. Now the planks have been removed in this particular condition. Finishing is going on. You can see these 3 masons doing the finishing of the top of concrete. And here you can see the pre-stitching cables here. Because this is a different view, they are basically orthogonal. Cables are in orthogonal direction. Reinforcement also orthogonal. Next dome is a OC dome. We talked about inner containment, the outer containment dome. Here the concrete is done from top to bottom. Almost the complete dome is completed. You can see curing is going on. The lowermost level of the concreting is continuing. Again, this dome also has been done in multiple pours. This is the last pour that they are doing. And here also we are using top formwork. Of course, this is not twisted concrete. It is normal RCC. And here we have the 2 NDCTs, the cooling draft covers, ready for commissioning. OC dome concrete completed. We can see one reactor building fully completed OC dome. Here, the next reactor building OC dome almost getting completed. The previous slide, the extension of the previous slide. Okay. Now, I'd like to talk about something about the testing of the containment. Now, let us say if you are a bridge engineer, you will construct the bridge. After constructing the bridge, you're going to do load test. Reason? Because vehicle traffic is going to move over it. So IRC gives you how to do the testing, what load do you put, and simulate the condition of the vehicular movement and have a static load and test it. Test it for what? Deflection and stresses in the bridge girder or whatever could be the bridge structure. Whereas in a reactor building, the containment wall, we don't have to test the slabs and walls, internal walls. We talk about only containment wall. Containment wall is tested for pressure. As we saw in our earlier slide, containment wall does not take any load of the slab or the wall. No internal load is getting transferred to the containment wall. But the containment wall is bound to experience pressure. Now, why the pressure has come, how it comes? The first one we call it as integrated leak rate test, ILRT. In a reactor building, let's say, we call this as actually incident. An incident happens, let us say. An incident, let us say, is called LOCA. LOCA full form means loss of coolant accident. Loss of coolant accident means the coolant gets drained out from the pipe, and the reactor starts heating up. Now, coming back to the coolant getting drained out, the loss of coolant which is coming out from the pipe and it's drained out from the pipe, this will be certainly highly active water. Okay, there's a lot of radiation in this water. Secondly, the pressure inside the containment starts increasing because this water is under pressure. Why isn't the pressure just come? Let me go back to my earlier slides. I told that water as a coolant enters into the reactor and takes away the heat. If you heat water, how much it can take temperature? It can go to 100 degrees centigrade. After 100, it becomes steam. But taking out just 100 degrees centigrade from the reactor is not going to be of help to us at all. So we pressurize water, increase the pressure of water, so temperature drawn from the reactor may go up to even 250 degrees centigrade. So high pressure water is passing through this cooling system. This, if it starts leaking out, it increases the pressure in the containment because containment is also a contained volume of air. So anything increasing pressure in the volume of air starts increasing temperature, increasing pressure in the containment. So the inner containment starts getting pressurized. Now, because this particular air is contaminated, we should not allow this air to leak out. So we conduct something called as integrated test. After the reactor building is ready, before commissioning, we conduct a test. So for a 700 megawatt reactor, the test pressure is 8.8 kg per square centimeter. And allowable leakage rate is 1% volume per day. What does it mean actually? 1% of volume is 1% of the contained volume. Within the containment, whatever is the volume, minus the volume of the equipment, the free air, free volume. So 1% of the contained volume in one day can be allowed to leak at 0.8 kg per centimeter square. Now, how do we do this? After the container structure is construction is completed, and before commissioning, we close all the exit points of the containment. We block all the doors, entry doors, and we pump in air. Just go on pumping air till you reach 0.8 kg. Once you reach 0.8 kg, there may be some leakage somewhere. Okay, so we go on adding air in more and more air into the containment to maintain 0.8. The amount of air that we added can be measured with a flow meter. That air what you're adding will be equal to the air which is leaking out. So measure this volume of air which you're pushing inside, and that air what you pushed in one day, 24 hours, not more than 1% of the contained volume. If let us say during the test we find this is more than 1%, we identify where that leakage has happened, and we basically go to every corner of the containment. We use soap solution, spray solution on the surface of the wall, and then we find out if there's any bubble formation, mark it, and post that release of air, reduce the pressure, and do grouting and repair that particular point where we are located the leakage and retest it. We keep on doing this till we achieve 1% volume per day leakage rate. This is a containment leakage test. Basically, this test is done once before commissioning and every 5 years after commissioning to ensure that the IRRT of the containment is maintained. The next is a proof test. Proof test is more of what we do in any building, testing of building. So it's nothing but structural integrity is maintained or not. This is what we need to find out. Again, the pressure of 1.84 is a very high pressure. Again, let me go back. I told 0.8 kg has come from loss of coolant accident. One more incident that can happen inside the reactor building is MSLB, main steam line break. Now, like I told in the earlier slide, that from the steam generator, steam is taken out through a pipeline, goes to the turbine. The reactor building and turbine building are far apart. But a part of this pipeline, because the steam generator is within the reactor building, part of the pipeline is within the containment. Outside the containment, we are not bothered. But within the containment, that pipe is passing through. If there is any break of pipe, rupture of pipe here within the containment, the steam is under very high pressure, it starts leaking out into the containment. It starts leaking in the containment, pressure on the containment increases, it may go up to 1.84 kg per centimeter square. At that high pressure, what happens to containment? We do all this monitoring. Settlement of raft. Now, if the raft is resting on a solid rock, then settlement may not be much of a criteria. But if the raft is resting on pile foundations, then there is a possibility that there could be movement of raft. So we check the settlement of raft during this high 1.84 kg per centimeter square. That means we pump air into the reactor building till we reach 1.84. Now, mind you, here we don't bother about leakage of air during this test because already that test is completed at a lower pressure 0.8. At 1.84, certainly leakage may happen. We're not bothered about that. But we are concerned about the reactor building or containment integrity test. So settlement of raft is one. Use simple survey equipment. We find out settlement of raft. Strain in concrete. We need to find out stress. So measure strain and work out stress. This is done by embedded vibrating bias to bias strain gauges. We call it as VWST. So when we are casting the concrete wall of the containment or the dome of the containment, we leave these vibrating bias strain gauges in the containment wall during concreting. We install them there. Wire is brought out through the formwork, make a small hole in the formwork and bring it out, leave it there. And these strain gauges are installed, embedded in concrete. Concrete is poured over the strain gauge. We always take care wherever there is a strain gauge, vibrator is not anywhere near that area, so this will damage the strain gauge. So all the strain gauge wires are then connected to control room, and from there we measure strain in concrete during testing, right up to 1.8. Dilation of containment. Containment is certainly circular. Dome is hemispherical. When you have a pressure inside, there is a possibility that the circular cylindrical containment wall will bulge out. Dome may also dilate. So to measure this dilation of the dome and wall, we use dial gauges and measure the dilation. The designer would have given us certain points on the dome and wall where to measure the dilation. We put the dial gauge on top of it and then measure the dilation of containment. Field measurement. Now, we told that reactor building containment is almost like a cantilever structure resting on the raft. If there is any small unsymmetry in this containment, small unsymmetry due to the pressure inside the containment, though the pressure is uniform, due to unsymmetry in the containment during construction, there could be tilt of the containment. So this tilt also is measured using survey equipment. Measurement of pre-stress. Now, as I told, IC containment, I said in the containment is pre-stressed. When the dilation of the containment happens, automatically the cable gets stressed more. Let us say the final pre-stress in the cable after all the initial losses is around 65%. During the testing, it may go to 70, 75, 80%. Or it may cross 80, we don't know, depending on the dilation. So to ensure that none of the cable are getting overstressed, we measure the pre-stress in the cable. But we cannot measure in all the cables. So we select 8 cables which have been kept symmetrically or all around in the wall, and we install load cells between the bearing plate and the anchorage unit. We install a load cell in the stressing gallery and we monitor the stress in the cable. The last is the crack measurement. If at all crack is visible on the containment wall, then we use a fender gauge to measure the crack. So these are the various monitoring methods and devices that we do for the structural integrity test or the proof test. This test is done only once after construction, before commissioning, whereas IRRT is repeated every 5 years. Okay. Now, the next slide is my last slide. I've shown a photo here. Most of you would recognize this photo. It's basically the Chernobyl reactor of Russia. You know very well, Chernobyl reactor underwent accident and there a lot of radiation came out from the reactor building. It spread in a large area and the radiation was there for quite a long time. The reactor building is, I would say, was here. And now it's no longer there because the slab is already blown out. The roof slab of the reactor building is blown out and thrown out onto the road. This whole thing became a gaping hole. This happened. Let me give a small brief about what happened here before I go further. I told you about loss of coolant accident. That exactly happened here also. But there is a change. What happened? They were doing R&D. The Chernobyl power plant engineers and scientists were doing R&D on the reactor. And during the process of R&D, they were in the process of draining out water once in a while. Control room was aware that R&D is going on. So at one point of time, somewhere water leakage happened, not due to R&D, but due to some other reason, water leakage happened. The coolant started leaking out, and the control room people didn't realize that this is actually happening not due to R&D. They thought because of R&D, some water is getting drained out. So they overruled the indication and they continued operating the reactor. At one point of time, the leakage happened so high that the reactor temperature went on rising very high. Mind you, the reactor, in the core of the reactor, the temperature can go up to, during operation condition, of normal operation condition, can go up to 2000 degrees centigrade. 2000 degrees centigrade. In case of accident, it can be much, much higher than 2000 degrees centigrade. Such kind of high temperature in the reactor caused the explosion, and that explosion blew the roof of the reactor building. The roof got blown out. Once the roof got blown out, the reactor was visible to the atmosphere, and all the radiation particles started emitting out into the atmosphere. And again, due to high temperature, fire incident occurred in the reactor building. A lot of fire was raging inside. So what the people of Chernobyl, our power plant engineers, what they did was to contain the fire. They brought sand in a helicopter and dumped inside into the reactor building to contain the fire. Now we have to contain the radiation. That's where civil engineers are stepped in. What civil engineers have done here is, now to contain the radiation, one of the material which I told about in our earlier slide, boron could be a material which could be used for attenuating the radiation. So what civil engineers have done here is, of course, not a new technology was developed, and that it was earlier being used. So it is another special concrete was developed, concrete with boron carbide. We call it as borated concrete. Mix boron carbide in concrete, mix it in a vacuum plant, bring it and dump it. But you cannot go near to dump it. So again, they used a helicopter. They took concrete in helicopter and dumped inside into the reactor building. Today, if you go to Chernobyl, you'll find a huge mass of concrete. So here we used another type of concrete, which is called as borated concrete. We use this borated concrete in a number of places in the reactor building, but not a normal practice. In certain areas where there's a small inaccessible areas are there, we use borated concrete for shading purpose. Okay, this was my topic for today. But today morning I got some suggestions by several of your engineers attendees that I need to talk about Unit 1 inner containment dome delamination. Yeah. Very.
There was a question now also. Yeah, the same question was put. Yeah, right.
I mean, it's a very a topic which debated a lot. Of course, this happened long back. I mean, more than a decade ago. But still, it's worth to know what happened there. Okay, so I'm going to take another 5 minutes, few slides on the delamination of dome. I'll be talking more on a technical part, nothing to do with the responsibilities at all. It's only technical.
True.
The Unit 1 of Kaiga. Now, Kaiga, today we have got 4 units, 1, 2, 3, 4. Unit 1 was the first unit, and we were always constructing 2 units at a time, pair of units. So, Unit 1 dome, IC dome, concreting was completed. Soffit formwork was de-shattered. We had removed the de-shattering, done the de-shattering of the formwork already. Pre-stressing, 35% of cables were completed. It is not partial pre-stressing, it is 35% of the number of cables. Around 180 cables were there in the dome. Out of it, 35% of the cables were stressed already. At 11:30 hours on 13th May 1994. And mind you, that was again 13th, Friday the 13th. Okay, on 13th May 1994, around 11:30 hours, there was a huge sound, and the whole building shook as if earthquake has happened. And because and that huge sound has come because of the central portion of the inner containment dome collapsed to half the thickness. I used the word in my previous slide as a delamination. I didn't say failure. I didn't say collapse there. It is actually delamination. Means the dome thickness is separated into 2 parts. The lower part half fell down, top part remained intact. So it got delaminated, and only for the central portion, the crown portion of the dome, that much portion got delaminated. The pre-stressing cables are there in orthogonal direction. The lower cable, which is below the central line of the dome, they got detensioned and became straight taut, because the cable like this has become straight because it lost some pre-stress. Cracks developed around the anchorage in the ring beam. Now, because the pre-stress loss, the detensioning happened in such a sudden manner, the anchorages in the ring beam on either side, those anchorages, cracks were developed around the anchorages. But of course, when we investigated, these cracks were not very major, they were quite minor. Okay, but still, some repair work were done there also. Now, just before I go to the next slide, I just want to tell something. When the IC dome, pre-stress IC dome, when we completed the concreting, We don't do pre-stressing unless soffit formwork is removed. Soffit formwork, if I don't remove it, if I keep the soffit formwork of the dome as it is, and I do pre-stressing because it's a curved cable, it will pull the concrete structure down because of the shape of the cable. When you go on stressing, it starts pushing the dome down. When it pushes the dome down, this soffit formwork will experience huge force, not at all designed for that force, and it may damage all the supporting structure below the formwork. And that's also not advisable. So we always remove the soffit formwork, allow the dome freestanding, then do pre-stressing. Okay. Now the dome on its own can stand without pre-stressing. Pre-stressing is required for our inner containment pressure. Nothing to do with the self-weight. The dome can stand with reinforcement on its own due to self-weight. Okay. When it comes to pressure, for that reason, because of the higher pressure, to avoid crack formation, we are stressing the dome on the wall and inducing compression in the dome on the wall. So that when the pressure comes up, the compression gets released and we don't come across any tension points. This is a photo which of course, we are not able to access any photo. It's out of bound, but this was available in the Google. But basically, it's quite easy because it looks like it's a photograph of photo. So in those olden days, we didn't have digital camera. So we would have taken a photograph on a normal camera, and then somebody would have clicked it and taken a photo. What you see here is, I had told the dome de-sheeting was completed. Okay. Now de-sheeting was completed, all the formwork was removed. But what you see, the red color structure here was a central tower. It was a temporary tower installed for supporting the formwork. The dome formwork was in the cloud shape. It was made of trusses. So the truss, one end was resting on the tower, other end was resting on the ring beam. So the central tower where the truss was resting, that was not yet removed. Dismantling was in process. You can see one part of the tower still on top. This part is removed out. So this tower was intact, was not removed yet. And you can see part of the dome, concrete dome, is resting on the tower. Let me tell you, this particular incident did not cause any mishap for human being. There are several reports in the paper that 2-3 people died and things. No, nobody died. Nobody died. Only one person was injured, not critically, first aid, and he was sent home. That fellow was actually doing some cutting and welding of this tower, dismantling. Okay, he got injured to some extent, but sent back home after first aid. Otherwise, there is no other injury happened to anybody. I'll tell you what exactly happened there. So this particular dome structure, the half portion of dome, is now resting on the tower. You can see all the pre-stressing cables here exposed. These cables have become straight. In the photo, you're not able to make out. They become straight already. Other direction cables are still intact in concrete. They didn't come out. The upper layer of cable didn't come out because half thickness they delaminated. In the lower half, cables have come down. Upper half cables, they're there as it is. Now, as I told you about mishap, nothing happened. The reason was simple. We had followed a lot of safety measures before casting the dome. Before casting the dome, to allow people to work in the lower floors, we had created a platform, a steel platform at around 10 meters below the dome, completely covering the reactor building, inside the building, fully covered with a steel platform. Now, whatever debris that fell from the top, the big chunk of mass is resting on the tower. It didn't fall down. But the pieces of debris fell on the platform. Nothing came down. So due to this, there were some openings where small things fell down, but then most of the debris was contained on the platform, due to which people who were working below were safe, completely safe. So it's one of the safety features which we employed here, that during construction, to segregate people working below and working on top, even some nut bolted falls shouldn't fall on people below, we have put a platform. So that saved a lot. Now, this is the same dome when you look from outside. Nobody can say that this dome is failed because the top surface is intact. Though there could have been cracks from distance, nobody can make it. These are ring beam anchorages, what I told you. Some cracks were occurred around the ring beam anchorages. But the top surface of dome was intact, nothing happened. The lower portion got delaminated. Let us go to the technical things. This is a plan of the IC dome. The dome is around 42-meter diameter. I mean, in plan. And we have got 4 openings. 1, 2, 3, 4. These openings were there in the 220 megawatt reactor, which is Tiger 220 megawatt reactor. We had 4 openings. Now we have changed it to a oblong opening, single opening instead of 2. We got 1 year and 1 year in 700 megabytes. Now, if any structural engineers is on board, they'll understand that opening in a shell structure is always attracting a lot of high stresses around the opening, and we always try to avoid opening in shell structures. This is certainly a shell structure and has got openings. So this particular opening was treated. How the thickness of the concrete around the opening, the section AA is here, is 1 meter thick. The general concrete thickness of dome was 340 millimeter. So around the opening, thickness was increased, reinforcement was increased, precessing cable band was added inside. So this opening was taken care structurally to ensure that no excessive stresses can happen. But what happened here? What happened was, as I told, that delamination happened. What you see the line here is the extent of delamination. You can see that zigzag line goes around, comes up to the opening of the steam generator opening in the dome, goes around the opening up to here, again takes a turn, again comes down, goes around like this, again it goes around the opening, again like this. So this portion completely got delaminated. Of course, some figures are given on the thickness of delamination. Let's not look at that part. So what I'm telling you is, central core portion of the dome got delaminated. The delamination initiated from around these SG openings. I am calling SG means steam generator openings. Around the SG opening, the delamination started and proceeded towards the crown, and it broke off this much portion. Now, what is the reason of delamination? You take any curved structure, curved in elevation. Okay? I'm talking about curved in elevation, similar to a dome. This is a curved structure, this thickness of the dome. Red color line is a pre-stressing cable. When you stress a cable, what you do, you pull the cable, the jack bears against the concrete, so bearing plate will push the concrete into compression, cable is in tension. This is a normal practice of pre-stressing. The cable is always in tension, the concrete is in compression. If the cable were to be horizontal, simply horizontal cable like in any of our flat slabs, it's simple, we just pull the cable and the stress and compression happens in the concrete. There is no eccentricity of this cable on this slab. Whereas in a curved dome like this cable has got eccentricity. In the sense the force is eccentric to the center of the dome here. So when this force is happening like this in a curved cable, there will be a pulling force, or the cable tries to straighten out. From here to here, the cable may become straight to straighten out. But because it's covered with concrete all around, it will apply pressure on the concrete. So concrete below this will experience pushing, and there will be a split happening between at this line above and below. We call this as radial tension. And when talked about split tensile strength, this is where we are concerned about split tensile strength of concrete, that in this portion, the split tensile strength of concrete should be adequate enough. So this radial tension of the cable pulling the concrete down caused delamination along this joint. I have shown one cable here, other cable was in the other direction. Okay, that is pulled in the other direction. But finally, lower cable was able to exert the load downward more, and the radial tension pushed the dome down. So half portion of the dome in this area got delaminated due to radial tension. Okay. Now, what improvement was taken? What was done to improve this? And what we did later? The reactor building 1 dome was completely dismantled. Up to the ring beam face, ring beam was retained. Up to ring beam, we completely dismantled it. Now for dismantling, we couldn't use any breaker. So we used core cutting machines, a chain of core cutting, and we completely removed the dome and removed it from there. Reinforcement, pre-stressing cable, sheathing, everything was removed. The dome was removed. So all the delaminated and good portion of dome, everything was removed and taken out. When that was removed and taken out, then the re-engineering was done on the dome. First thing, I told cracks were formed on the face of ring beam. To avoid any further dissipation of this crack, the ring beam was pre-stressed externally. Of course, this was done after casting the re-engineered dome. External pre-stressing was done on the ring beam outer face. I think 4 tables were laid around and external pre-stressing was done. Coming to the dome, what change has been done? The pre-stressing cable spacing was changed. Earlier, we used to have cable spacing as close as 100 to 120 millimeters. Then in the re-engineered dome, the minimum spacing was 225 millimeter. And that 225 millimeter was kept near the openings only. Close band of cables near the opening only to take care of stress concentration. Balance portion area was 450 millimeter spacing. in that range, 450 mm range spacing. So we got more space for pouring concrete. Reinforcement pattern. In the earlier dome, the reinforcement, like any other dome, it was in circumferential and meridional direction. Radial and circumferential direction. In that direction, the reinforcement was laid. Now, in the re-engineered dome, whereas the cable earlier also was orthogonal. So, cable orthogonal, reinforcement in meridional and circumferential direction. Whereas in the re-engineered dome, reinforcement also was made orthogonal. By doing so, what we did was we were able to put reinforcement below and above the cable. And this reinforcement, top and bottom mat, was tied with radial ties. By tying the bottom and top mat, we were able to achieve whatever is shown here, the radial tension was taken care by the reinforcement. The reinforcement, tying reinforcement was not very big diameter. I think we use around 10 and 12 mm diameter rods. In some places 16 mm, always mostly 10 and 12 mm diameter rods were used. So these rods were at every junction cross section of the reinforcement, we used to put one tie. So this tie was introduced to take care of the radial tension. Grade of concrete was changed from M45 to M60 to improve its split tension capacity. And RCC-G code was brought into picture. Earlier, we were not using RCC-G code, we were using IS code. But by bringing RCC-G code, we are not improving, changing the properties of concrete. Everything is same. But the qualification criteria were made more stringent. Quality control, quality assurance measures were more stringent. And supervision at site was made more stringent. Subsequently, after casting the dome, same drawing and same method was used in the Unit 2 dome also. Both were tested and they are passed. And here this photo shows the reactor building today of Paiga 1 and 2, standing there producing power 100%. Recently, we broke a record of operating plant for more than a year. Is a world record. Thank you. Thank you very much, ladies and gentlemen. Thank you for having this patient to me. I went into civil engineering, physics, chemistry, mathematics. I don't know whether I bored you, but I'm sure I would have told you certainly something about nuclear engineering and use concrete in nuclear power reactors. Thank you.
Thank you so much, sir. It was a wonderful presentation. In fact, you have cleared two of the major questions in your presentation itself, and you have also mentioned how it can be avoided and what were the reasons behind that in a very crystal clear terms. In fact, there was some doubts among the participants whether these questions would be answered. In fact, before asking the question itself, you have taken because actually what happens is that failure stories are ones which can teach us lessons.
Exactly.
That is what is more important.
Should be a stepping stone. Understand the failure, learn from failure.
Learn from the failure. So
that responsibility is not important here.
Correct. So that you have brought out very well, sir. And in fact, you have covered all the aspects of concreting in nuclear power structures, which is really an eye-opener. Thank you for that presentation. Only thing is that can we have one question? Because
certainly, I mean, why one any number question? You can tell. Just I'll take some water. Give me some. I'll take some water.
Please. One is any particular reason for giving a dome shape to the structure? You are speaking of the dome shape. Why dome shape? Why not any other?
Yeah, fantastic.
And the second question is, what is the expected service life of a nuclear power station?
Fine. Dome shape. Now, as I told, inner containment and outer containment. Let's talk about the inner containment. The word itself says is containment. It is used to contain the high pressure air inside. If you take a curved structure, a circular or a hemispherical structure, the air pressure inside causes only hook tension. In the concrete structure or in the concrete wall or the dome. It doesn't cause any bending moment. If simple, let us say I go for a water tank. If I go for a rectangular water tank and fill water inside, the corners of the water tank will experience negative bending moment and positive bending moment in the middle span. If I put a circular water tank, the forces are only hook tension. Actually, hook tension, understanding and attacking hook tension is much easier because I'm using precessing cables. Hook tension is not good for concrete because it's directly causing tension. But I'm using precessing cables and I'm stressing the wall and the dome, introducing compression, built-in compression in the wall and dome. During the process of this increase in the pressure, this compression not become minus and become tension. It can reduce and become maybe zero. So having a curved structure for containment wall or a containment dome is always better than having a flat roof or a rectangular wall. The second question was, what was it?
Expected life of the nuclear power structure. No?
Well, when I say expected life, there is nothing called a number. We can't give a number to expected life of the nuclear power plant. How we decide a nuclear power plant life or its age or its capability is that we assess the plant. Like I told, every 5 years we do testing. Similarly, we do assessment of the plant and find out whether it is fit to operate further. Assessment is not done by one group of or two group of people. It is actually done at site level, at the operation level, and all the reports are sent to Atomic Energy Regulatory Board. They also come and inspect it. After taking a conscious decision, the operation, further operation of the reactor is allowed. So basically, like, if you look at, say, Tarapur plant, Tarapur 1 and 2, let me talk about Tarapur 1 and 2, which is a very old reactor. Today is still operating. It is that reactor was, I think, around 1960, still operating after 50 years, 60 years, but at a reduced power. So what we do is, if at all we find that, see, the life of a plant doesn't depend just only on the concrete structure. It depends on the equipment and the piping and other things which are inside the reactor structure. Some of the equipment, some of the piping in the structure cannot ever be replaced. Throughout its life, we cannot touch them, we cannot replace them. Such equipment and such piping or such items which are in the reactor building, they are assessed for their life performance. If the performance is going down, we reduce the capacity of reactor. At one point of time, let us say we find performance has gone way below and we cannot do anything, say we cannot even replace anything, then we shut down the reactor. So reactor life will be based on assessment every 5 years and then next 5 years. So it's like taking a fitness certificate for a vehicle. 5 years you do a fitness certificate and take another 5 years fitness for vehicle. Similarly, we take fitness at every 5 years.
Thank you so much, sir. Having been associated with Nuclear Power Corporation of India as well as L&T, you have got such a practical exposure that you have really spoken with passion and those practical aspects. And that was really wonderful, because many of the attendees, many of the construction professionals who had logged in were just throwing praises. They were saying that this is the best presentation webinar that they have attended. Many of them were. So I think,
Thank you, friends. Thank you.
Thank you so much, sir, for your time and for clarifying the questions and sparing your time. In fact, you have almost taken double the time which you are scheduled. So we're very thankful to you for that.
Okay.
Spending your time, and it was really an eye-opener, very knowledgeable webinar which was delivered by you. And I'm sure that it will be a memory for all of us, and we would be just remembering all this, and we'll be going back. Many of them, I'm sure, would have taken notes also. The way you were speaking and all that. Thank you so much, sir. Thank you.
I mean, anybody got a question? Certainly they can check with me. Okay.
Yes, sir. We'll pass on through email to you if there is any.
Certainly, sir. Certainly.
Thank you so much, sir. Thank you.
Thank you. Thanks, sir.